Very similar to the polarizability is the conductivity of a material. The conductivity is like the inverse of the resistance. If you apply an electric field, you expect a certain amount of current to occur. And for exactly the same reasons that you can have directional dependence in materials of polarizability, you can have directional dependence of conductivity, and so you end up describing the conductivity with a rank 2 tensor once again, this sigma. Stress is another one. If you take a jelly and you cut it, you'll find it doesn't just break, it also deforms. And that deformation is a sign of forces inside that jelly that have some tangential component to surface areas. The magnitude of the force is still going to be proportional to the size of a surface area. And so the relationship between a surface and the force is going to be a tensorial relationship. And that tensor is called the stress. There are a large number of other physically important tensor quantities. One is called the strain. If I have a stress in a material, then that might cause it to deform. An infinitesimal deformation is characterized by another second-rank tensor called the strain. That's particularly interesting for us because there's often a relationship between the strain and the stress, obviously, and provided the stress is low enough, and for many materials, that relationship is actually linear. Why is that so interesting? We've had a lot of linear relationships. It's interesting because the number of indices involved. Because I need two indices to describe my strain, and I need two indices to describe my stress, then the linear relationship, the most general linear relationship, has to have four indices here. And this thing here, because this has a physical interpretation as a geometric object, and this does too, so does this. So this thing here is a rank 4 tensor. The potential energy involved in causing this kind of deformation is just, again, just the force times the distance. And so you end up, you can show that this is just this particular combination. So again, you can use this rank 4 tensor to condense these two rank 2 tensors down to a scalar, or you can use it to convert a rank 2 tensor to another rank 2 tensor. And I was going to say, here you could do everything with a rank 2 tensor that you could do with a matrix. Well, with this you can do lots of things you can't do with matrices, but basically any kind of sum will produce the appropriate size geometric object as well. Finally, let's have a quick look at everybody's normal first tensor, the moment of inertia. So the moment of inertia I, we probably first found it in terms of a relationship between the angular momentum and the angular velocity perhaps, or maybe it was between the torque and the angular acceleration. However, of course, the angular velocity around a given axis is just a number, and the angular acceleration around a given axis is just a number, but we define that axis by making this a vector. And of course, the angular momentum is also a vector, and the torque is also a vector, r cross f. So this thing here, either it's constant for all axes, which we know it isn't, the moment of inertia depends on which direction and which axis you choose, or it must actually be a matrix, and therefore this is a rank 2 tensor. The moment of inertia is a rank 2 tensor. And that's in fact true. What that means is sometimes you can apply a torque on an object and it will actually accelerate around a different axis. It will actually start spinning around a different axis. That's true. And the relationship between the angular velocity and the angular momentum, they can also be different axes in general. We don't normally encounter that because we normally deliberately pick our axes to be the principal axes. This must be a symmetric tensor, and indeed symmetric tensors have principal axes. They have axes at which this matrix is diagonal, and we normally do our analysis around those things. But in general, it doesn't have to be. If we calculate the kinetic energy, for example, the kinetic energy in a rotating object, it's just a half mv squared for all the different pieces, and a little bit of work you can show that that is of that form, and you can go ahead and calculate the components of the moment of inertia if you know where all the mass distribution is. And we're not going to bother going into that because that's really a fairly straightforward exercise that you do when you're doing a messy particular problem. And indeed, all of these tensors that we've introduced here are not things that we're going to be using in great detail. Tensors are, however, all throughout large chunks of physics and engineering, all through material science. There's a lot of tensors used in fluid flow and climate models and geoscience and aerodynamics and so forth. There's a lot of tensors in electromagnetism. We're going to be encountering it in terms of special and general relativity as well. And they're also quite important to the fundamentals of particle physics and cosmology. So we really do need to know about their existence, but at this point we're just introducing the idea. They're geometric objects with more indices than just a single index like a vector.